The floor is yours.
Okay, thank you for the introduction and thanks for the invitation. So the topic today is the motivic image of J spectrum, and I will talk about how to use the effective slice spectral sequence to calculate it. And this is joint work with Eva Belmont and Dan Isaksen. And here is an outline of my talk. So this image of J story, actually the starting point is in the classical stable homotopy category. I will first talk about this classical story. So there is a thing called image of J spectrum, and it has some close connection to the stable homotopy groups of sphere. It detects classes in the stable homotopy groups of sphere. And then I will talk about how to build the motivic analog, what the motivic definition of this image of J spectrum is, and how it compares the classical case. I will talk about the computations using the effective slice spectral sequence. And at the very end, I will say a few words about what these computational results tells us, because our starting point is a classical story. So you may expect that certain things that's true that you see in the classical case, you may expect them to also hold in the motivic case. And some of them are true, some of them are not. And what we can get out of this, that is the last thing I want to say in my talk. Okay, so another thing is some convention I use in this talk, that is when we work two primarily, that is most of the things, they will be either too local or too completed. I will say them, I will try to remember to say them, but I will not include this to local or to completion notation the subscript in my notations. Okay, so let's start with the classical story. So the story starts with this map called J homomorphism. The J homomorphism is defined as follows. So first you can look at the orthogonal map from the n-dimensional real vector space to n-dimensional real vector space. And if you compactify that, then you will get a self-map from Sn to itself. And this gives a map from On to loop n Sn. And these maps for every n, they're compatible after you pass to the homotopy groups. So if you take n to infinity, you will get a map from the homotopy groups of O, the orthogonal group, to the stable homotopy groups of the sphere. And this is the J homomorphism. So this J homomorphism is important because, well, it's some geometric thing, and also it detects certain elements in the stable homotopy groups of the sphere. And later, a spectrum called little J spectrum or image of J spectrum is constructed. And well, it's constructed such that this spectrum, its homotopy groups see the image of this J homomorphism, and it is defined to be the fiber of this map. This is everything is too local here in this definition. And then let me explain what the notation means in this definition. So here KO is a connective real K-series spectrum, and KSP is a connective quaternionic K-series spectrum, and this Kasai cube is an Adams operation. So the classical little j is defined to be the fiber of this map. And let's take a closer look at what these things are and what the homotopy groups of these things are. So first, for KO, we have the plot periodicity, which tells us that the zero space of KO, the real K-series spectrum, is Z times BO. And if you take loop of that, that gives you the first space of this spectrum. It is O. And if you take loop, you will get O quotient U, and it continues until the eighth one, and it repeats. So this is a periodicity of the real K-series spectrum. And this is a zero space of KO. And this is a zero space of, oh, each time I say K Siri, my Siri will respond. Sorry, let me turn it up. Okay, so this is a zero space of the real K-series spectrum, and this is a zero space of KSP. So in other words, you can see from this eight periodicity here, KSP is KO shifted by 4. So if we take the force suspension of KSP, then it is a force connective cover of KO. And if we go to homotopy groups, we have the sum to help us memorize the homotopy groups of KO, that is Z2, Z2, 0, Z, 0, 0, 0, Z, and it repeats. And this is the homotopy groups of KO. And KSP, it's a force connective cover, so everything before 4 is 0, and you start at 4. And everything else is the same as KO. And this is a homotopy groups of KO and KSP. And remember, we define J to be the fiber, so we can do a long exact sequence calculation to get homotopy groups of J. And for that, we need to know how the Adams operation -1 acts on these homotopy groups. And it is times 8. I wrote it here. It is times 8 on the degree 4, and it is times 16 on degree 8, and everything else, for at least in the range I wrote here, it's 0. It's trivial map. The Adams operation -1 is a trivial map. So we calculate the homotopy groups of J using some algebra. So for example, this Z mod 8 here in degree 3, it is what the co-kernel in this degree 4 contributed to. Okay. Yeah, so the purpose of writing out the homotopy groups of J here is that I want to compare it to the following chart. So this is a part of the classical Adams-Noikov spectral sequence for the sphere spectrum. And the thing that this is a part of the E infinity page, and the thing that I include here, I call it alpha family. You can see that the image, the homotopy groups of J, it catches the alpha family. So for example, degree 1, it is a dot here, which means a Z mod 2, and degree 1 here, it's Z mod 2. And degree 2, you look at, you look at that there is only one dot here, so it's also Z mod 2. And degree 3 here, maybe it's too small, but this dot has a 2 decorating it, meaning that this dot is Z mod 4, Z mod 2 to the power of 2. And with this red extension to the top dot here, they form a Z mod 8. And that is this Z mod 8 in degree 3. And you have 0, 0, 0, and this is a dot decorated with a 4, meaning that this is a Z mod 16. And I'm not going to do more comparisons, but yeah, but the thing I want to point out here is that the homotopy groups of little J spectrum, it catches these alpha families in the Adams-Noikov spectral sequence. Okay.
Sorry, Hana, just to clarify, this is the E infinity page of the Adams-Novikov spectral sequence for the sphere.
Right. Yes.
Uh-huh.
Yeah.
Is there is there a map in one direction? Let's see.
Right. Actually, there is, I forgot to say this, but I want to say that the sphere to J is a surjective, how to say, the Hurwitz map induces surjection on homotopy groups.
Oh, I see. And we can also see that in the spectral sequence, right? Or can we? Let's see, could we read that off the spectral sequence? Let's see.
So
are there extensions here, or there's no extensions?
The extensions you mean, so like the extensions in Adams-Noikov spectral sequence, this part they're drawn out using this red lines. These red lines are two extensions.
Okay. Oh, so that's the extension problem has already been solved here.
Yeah.
Okay, thanks.
Right, and then if you look at this map from, let's see, there is an honest map from the sphere to the image of J spectrum. And
Mhm.
you said the statement is that on homotopy groups, it's surjective. And I'm wondering if we can see what it does on E infinity pages of the Adams-Novikov spectral sequence, or at least, well, basically the classes that you described are those that, well, that survive that map, right? They're in the image of J spectrum, the homotopy thereof.
Right. So I think you can do the same thing. So you can run the Adams-Novikov spectral sequence for KO and KSP. And well, you can, this is not entirely correct, but if you get the Adams-Novikov spectral sequence for KO, KSP, and then you do this, you think about how the Adams operation acts on it, and you get the Adams-Novikov spectral sequence for J, and that matches the alpha family picture for sphere.
Okay, thank you.
Mm-hmm. Yeah, right. So this is a classical story. Thanks for the questions. And then let's do motivic. What is a motivic analog? So motivic here means that we are now in the motivic stable homotopy category, and the notation is SH of K. I'm not going to talk about detailed constructions, but you can think of it as some variation of the classical story. It is the classical category. It is some combination of topological things with algebra geometric objects, and this field K, it is where these algebra geometric objects, they live over. And this category has lots of good properties. For example, it is symmetric monoidal, it is stable, and you can do all the homotopy theory techniques in it, like spectral sequence calculations. And also the connection between this category and the classical category is that when your base field K is good enough, you have a functor from the motivic category to the classical category, and it recovers information in the classical category. Okay, so, right, so in this category, if we want to do the motivic analog, then of course, we want to make the analog of this definition of classical J. Somehow I cannot select the whole thing. Okay, this definition is as a fiber of this map. And this is done by Bachmann and Hopkins. They define the motivic little j to be a fiber of some similar map. And here I'm abusing notations. I'm using this blue thing to denote the classical spectrum and the classical map, the classical definition. And this is, everything is motivic in this selected equation. And from this slide, after this slide, everything will be motivic. So hopefully there will be no more confusion. So every J after the slides or KO after slides means a motivic thing. And now what are these, what are the things in this motivic definition? So of course, KO, KSP, and this Kasai cube minus one, they're the motivic counterpart of the classical thing. And KO, it is the motivic spectrum, the very effective motivic Hermitian K-series spectrum. So the motivic Hermitian K-series spectrum, that is analogous to the uppercase KO, the real K-series spectrum, and this very effective means you take the very effective cover of that, and the very effective cover plays the role of taking the connective cover. So that is the motivic KO. And the motivic suspension 4-2 KSP, this is the second very effective cover of the motivic KO. And this definition is analogous to, in the classical case, we have suspension 4 KSP is the fourth connective cover of KO. And
sorry, Hana, I'm more familiar with the effective slice filtration The very effective one is the one that's not given by triangulated subcategories, right? It's not
Right.
automatically closed under D-suspensions, topological D-suspensions, right?
Right. Yeah.
Uh-huh.
Yes.
And
Yeah.
what's the benefit? Is it computationally better behaved if you take the very effective
Oh,
filtration?
yeah. So if I take the effective, so for example, in this case, if I take the effective cover of the uppercase KO, the Hermitian K-series spectrum, there will be some extra saying in the zero slice. So this is a paper by Tom Bachmann. He talked about if you take the effective, the effective slices of uppercase KO. And another thing that is good about this very effective cover is that it compares well with the C2 equivariant slice filtrations. So like for MU, KU, and like these, I think these even things you can take and you look at R-motivic, C2 Betty realized to C2 equivariant, then the very effective filtration, the very effective slices realizes to the equivariant regular slices.
On the nose, or there's just a comparison between the two? I was just thinking about that recently, and my hunch was that at best there would be one inequality. But are you saying that you get the nth slice here after you Betty realized, you get the nth slice of the Betty realization? Is that?
Yeah,
or you just get some inequality that there could be a shift in one direction?
you get I think on the nose it's not maybe there's a times two, like two speeded, or the filtration is everything times two or divided by two.
That'd be harmless. Yeah, I would be fine with that. I was just more worried that there could be a shift in filtration.
No, I don't think there is a shift, but that's only true for things like MU, KU.
Oh, okay. Just for certain motivic spectra. Got it. Thank you.
Yeah, this is in the paper by Drew Hart.
Okay, great.
Yeah, and right. Okay. So yeah, I'm not going to in my talk about the definition of very effective cover. So the only thing I use is that they are used to define this motivic KO and KSP, and they should be thought of as the motivic analog of taking the connective cover here. Okay, so that's a definition. And then our next question is, okay, we have this definition and we have the motivic sphere, and how do this J and the motivic sphere, how do they compare? Whether the classical story happened in the motivic case. For example, you may expect that from the sphere to little j, this is a surjective map on homotopy groups, or you may expect that maybe the homotopy groups of this motivic J has something to do with Adams-Novikov spectral sequence or some motivic alpha families, things like that. And to answer these questions, we need to talk about computations. So computational tools for the motivic sphere, I listed two here. One is the motivic atom spectral sequence, and the other is as in the title of this talk, the effective slice spectral sequence. The second one is the main computational tool for the little j spectrum, but I would like to first show say a few spend some time on the motivic atom spectral sequence to show like how in the motivic case, how the spectral sequence calculation works. So one thing that is special in the motivic case is that the motivic spheres, you have bigradings for motivic spheres. There are two kinds of circles. One is called Tate circles. This is in the motivic world. This is a alpha line minus zero, and this is a more algebra geometric object. And the other one is the more topological object. It's called it's called topological circle or simplicial circle. And by smashing these two circles together, you get all kinds of bigraded spheres in the motivic category. And because, so maybe let me first explain the grading here, so S is what we call stem, and W is what we call the motivic weight. And the motivic atom spectral sequence, it looks almost the same as the classical atom spectral sequence. You just need to replace everything using their motivic analog. So for example, here, this HF2, it is the motivic Allenberg-MacLane spectrum. And this A here is a motivic dual sting rod algebra. And these things, they are well studied. For example, Martin has this paper with Spatzerweg on the motivic dual sting rod algebra for positive characteristics. And in many cases, they are known, and you have closed form formula for them. So this E2 page is something you can actually compute. And a difficulty in the motivic calculation is that you may have noticed that things are trigraded here. That means the spectral sequence, each page is a three-dimensional thing. So to draw them nicely on papers, we need to choose some projection. And here we organize everything by co-weight. So co-weight is the stem minus W. So for example, the E2 page, which will be a lot of charts, and each charts represent a single co-weight. Okay, so we have this three-dimensional E2 page, and you just chop it according to the co-weight. So that's how we do the motivic atoms or motivic spectral sequence, trigraded spectral sequence calculations.
And sorry,
yeah, go ahead.
No, I was just going to say each page they're all independent, so the differentials just stay on each page. They don't go between pages.
That's very unfortunate, not true. So for atom spectral sequence, and for later I will talk about the effective slide spectral sequence, the differentials, they will bring the co-weight down by by one, bring it down by one. So it will be -1.
Oh, but that means that they do preserve the weight, right? If you just keep track of the trigrading, so D goes from some weight to the same weight always.
Yeah, the weight will be the same, but there are some advantages about organizing by co-weight, because there are two very important permanent cycles. One is eta, the H1, or the other is rho. They are in co-weight, so you want to draw these things on the same page.
I see. Okay, thank you.
Okay, yeah, thanks for the questions. And yeah, I put here some charts. This might be too small, but this is a co-weight sorting charts and for the R-motivic computation. And you see that there are these regular patterns to parallelograms and also I include the co-weight 11 chart. Yeah, so the point of I putting these charts here is not to explain details in the charts, but show how the picture looks like. And the thing I want to point out is that you have these kind of regular patterns happening every 4-2 or 8-4 degree. So in the co-weight 11 picture, you have this staircase lapsing, and it continues. So these blue arrows, they're infinite H1 towers. And also you have some garbage here. These are not that regular. And yeah, so this is co-weight 11. And if we look at co-weight 4 smaller than that, which is co-weight 7, you also see this staircase-like thing. And now you have 4 arrows instead of in the co-weight 11 picture, you have only 3 arrows. So this is complicated picture, and you might want to simplify that. And one way to simplify it is just count how many arrows I have. So that is, if I invert this class, which is eta, so eta is this blue multiplication arrow. If I invert eta, then what remains are these non-eta torsion part, or these eta torsion part, they will die. And what remains are these arrows. So this eta-inverted phenomena, it is already studied by many people over different base field. This is motivic. And if you look at their answers, then the eta-inverted phenomena, the eta-inverted result in the answer, there is some image of J-style pattern. So this is one reason why I want to mention this eta-inverted case, eta-inverted phenomena in the atom spectral sequence here. And the other reason is that in our calculation, we use the eta periodic result to analyze our differentials, which I will mention later. Okay, so here by this image of J-style pattern, what I mean is that you will see some connection to the classical image of J spectrum. And what is the connection to the motivic J spectrum? For that, we need to know the motivic homotopy groups of J, and we use the effective slide spectral sequence. So yeah, this page of the slides is some crash course on the effective motivic effective slide spectral sequence, and it is constructed as follows. So first we have a subcategory of the entire category. It is called the effective category, and it is defined to be the smallest triangulated for subcategory containing all the suspension spectrum. And you have this category, and you can take suspension Q, 0 of that. This includes into the large category, and you actually have an adjunction. So the left one is an inclusion, and the right one is colocalization. You have such an adjunction, and you compose them, you get the Q's effective cover functor. So this is in analogous to in the classical stable homotopy category, we have the connective cover functor. And for any motivic spectrum X, we can use these effective Q's effective cover functors to build a tower. So this is the associated effective tower for X, and we can also get the associated graded slices. So for example, this Q+1 slice, it is defined to be the fiber of this map from Q+1 stage to the Q stage. And this is analogous to the Whitehead tower or Postnikov tower in the classical stable homotopy category. And if we take the homotopy groups of these associated graded slices, so that is some sort of Atiyah-Herzberg spectral sequence, this gives the E1 page of the effective slide spectral sequence. And if things are good, then it converges to the homotopy, bigraded homotopy groups of the spectrum, the motivic spectrum you start with. And yeah, I think as Donna asked before, the differential, the grading for the differential, how it works is that the R's differential bring the stem down by 1, bring the filtration up by R, and keeps weight the same. And in particular, on co-weight, it brings it down by 1. So if you organize everything by co-weight, you need to see, well, I was talking to someone that this is like if you think of everything using the Adams joke that spectral sequences are Shakespeare tragedy, because on each page you have lots of dots killing other dots or get killed by dots. So that's every time you turn a page, lots of things dies. That's describing a bi-graded spectral sequence, and in this tri-graded spectral sequence, this is more like a Shakespeare tragedy collection because you have a lot of books, And each character, they'll need to go out of their own book to kill someone in the next book. Does that make sense? So this is something weird and add to the complexity in the trigraded spectral sequences. When we do our computation, we need to put two co-weights charts side by side and see, okay, this co-weight n chart, how the differential goes into the co-weight n minus 1 chart. Okay, yeah. So actually, I include an example of the slice spectral sequence for KL. And so the slice spectral sequence for KL, we start with the slices for KL, and that is analyzed by, that is given in work of Ananevsky, Ronings, and Osberg, and they have this formula for slices of KL. It can be represented by this Allenberg-MacLane tensor with some polynomial algebra. And the meaning of this can be depicted in this chart. So this chart, so here this alpha 1 is in degree 1, 1, and V1 square is in degree 4, 2. And this chart is a visualization of this polynomial algebra. So you have alpha 1 in degree 1, 1, V1 square in degree 4, 2. And how to read of the slices from this picture is the following. So if I would like to read of a slice, the first slice, then I look at this horizontal line at height 1, and you see this only one dot alpha 1 here. That means the first slice is some suspension, the 1, 1 suspension of HF2 index over alpha 1. And similarly, if I would like to read of what the second slice is, then the second slice is you look at this horizontal line, there is 1 dot index over alpha 1 square and another square index over V1 square. And the dot is a HF2, so that is this summand, and this box is a HZ, that's the other summand, and the suspension depends on the degree of these classes. This is a 2-2, this is 4-2, and that's why it has 2-2 suspension, it has 4-2 expansion. So in other words, just to summarize what I just demonstrated is that from this slices of KL, you can, from this formula, you can draw a picture which helps you to quickly read of what each slice of KL is and present that in this picture.
Sorry, Hana, just to clarify what the chart is depicting, you're saying that that's the chart for the slice spectral, effective slice spectral sequence for KO, right? And it's the E1 page?
This is the slices. I haven't taken the homotopy groups.
Okay. So it's not part of a spectral sequence yet, or
yeah,
is it?
it's just I think it's so it's my preferred way to present the slices for KL.
Okay, so far it's just a convenient way of combining all the slices in a coherent picture. Yeah. Okay,
yeah,
it's not displaying differentials in some spectral sequence yet.
No.
Okay, got it. Thank you.
Sorry, when you say HZ, like what kind of object is that? That's like a graded abelian group or something, or?
Oh, sorry, I think I forgot to say it. So HZ is a motivic Allenberg-MacLane spectrum.
Okay, so these equations are of spectra.
Yeah.
Oh,
so
okay.
This is the right-hand side is kind of well, not that rigorous because it's spectrum tensor with some algebra. But what it means is that in this algebra, each class contribute to the slice of KO, contribute to Allenberg-MacLane spectrum to the slice of KO. Yeah.
Okay, Thanks, thanks.
Yeah.
And on that topic, to conclude about the structure of the slices, are we implicitly using the fact that each slice is canonically an HZ module spectrum? Does that fit into the picture? Or was there an a priori way to know right off the bat that the slices were given as those wedge sum ends, those wedge sums?
Yeah, I forgot how they prove that.
But I think, let's see. So if we use the fact that each slice is canonically an HZ module spectrum, it certainly makes the statement more plausible, right?
Right, yeah. But I
so-
think that is proved before their result.
I
Yeah,
see.
this is proved that the zero slice of the sphere spectrum is HC. It's proved earlier than Ananevsky, Rodnik's, Osver's paper.
Right, which is why I'm thinking that they could use that fact,
Yeah.
and it might be used in the background, but okay.
Yeah.
Thanks.
Thanks for that comment. Right, and if we add some ingredients to this picture, then we will get the E1 page. That is, so on this picture, everything is actually a spectrum, a motivic spectrum, and we need to replace these motivic spectrum using their homotopy, bigraded homotopy groups. So there are only two kinds of Ellenberg-McCain spectrum here, either HD or HF2. And the bigraded homotopy groups of HD can be represented by this picture, and for HF2 represented by this picture, so that to replace everything here using their bigraded homotopy groups, you need to draw a three-dimensional picture. So I'm adding a third plane, the XZ plane, and making this whole picture three-dimensional. And for example, this is a HD. Now I need to replace it using its bigraded homotopy groups. I just copy paste this picture, move it to the XZ plane, and make the original point put that at the place of this box. And if I do that to every dot and every other box, I will get a three-dimensional thing, and that is the E1 page of KO. Okay, yeah, I hope this picture makes sense. And and the E1 page of KO is tri-graded, and we can organize them by co-weight. In this case, it turns out that the co-weights are kind of too periodic. So the odd co-weights are like this pattern, and the even co-weight are this pattern. Okay, so in this example, this is just an example of KL, the effective slice spectral sequence of KL, and the input is that we know the slices, and we can produce the effective slice spectral sequence E1 page of it. And then let's talk about the computation for J. So we compute J using the effective slice spectral sequence, and that includes several steps. So first we need to know what the slices of J, what they are, and then from the slices of J, we can do what we just saw for KO. We can get its E1 page. And then from E1 page, we need to analyze the differentials. And after we analyze all the differentials, we get to the E infinity page. Now we need to know, well, are there any hidden extensions? And the last step, which actually should be the first step, is that we need to show that, okay, the thing we calculate is actually, it is relevant to J, and our spectral sequence do converge.
Sorry, Hana.
Yeah.
On the previous slide, you were saying that you're doing some R-motivic computations, and I was wondering if it's easier to work over the complex numbers first. At least I know in some contexts, it's simpler to work over C, and then you just crank it up and try R-motivically. Is there something like that here? Or?
Yeah, the C-motivic is easier. So in the C-motivic case, you don't have these red arrows.
Oh, I
Yeah.
see.
Yeah.
And in terms of flow of information, is it useful to start with the C-motivic picture and try to then move on to the R-motivic picture, or do you start right away with the R-motivic picture?
So in our calculation, we started right away with the R-motivic picture, but we did take a look at the C-motivic picture. C-motivic picture is easier, and it is actually helpful so you can compare the R-motivic picture with the C-motivic picture. C-motivic is easier.
Right, via the map from spec C to spec R, it induces a comparison map, right? Yeah, okay.
Yeah. You can, for example, some of the hidden extensions can be proven using the C-motivic information, but they can also be proven using other method.
Oh, okay, great, thank you.
Okay, yeah, right. So these are the 4 steps in the computation of the little j, and the theorem. And so what we did is that we calculated the bigraded homotopy groups of the R-motivic J using this motivic slice spectral sequence, and this calculation, the result can be presented in charts or tables or closed form formulas, but the closed form formulas, they're not very good looking. I find that charts are the best way to present these results. Okay. And how we did each step. So for the slices, this is just some sketch. For the slices, how we introduce the slices of J, we use knowledge of slices of KL, slices of the suspension for 2 KSP, and what we know about the Adams operation. And for the differentials, there are 2 kinds of differentials. One is D1 and the other is or higher differentials. So the D1 differentials, they are actual maps between the slices, between spectrum, the connecting homomorphism, so that they can be analyzed using these actual maps between homotopy groups, between spectra. And the higher differentials, they are analyzed using the eta-periodic result by comparing eta-periodic result. So that's differentials. And for hidden extensions, so we just talk about this. Hidden extensions, they can be proved using either comparing KL suspension for 2 KSP or by comparing to the C-motivic picture, or some total bracket messy product arguments. So there are different ways to prove hidden extensions, and they can all be solved, be determined. And for the relevance and convergence problem, we showed that the thing we're computing the spectral sequence, we're computing, it actually converges to the 2 completed little j, the bigraded homotopy groups of the 2 complete little j. So yeah, this is what we did. And let me show some charts. So this is a picture depicting the slices of J, and the left-hand side is J, the right-hand side is the effective slices of the sphere. And I highlighted 2 arrows. And the reason is that, well, you can see that these 2 highlighted arrows, they're not in the slices of J. And what the slices of J is looking at, it's looking at these arrows that start with these alpha n or alpha n slash some number, these elements. And these alpha elements, they're actually the alpha families. So why the alpha family names also appear in the effective slice spectral sequence, that is because the effective slice spectral sequence for the sphere, its slices, the slices of the sphere can be represented using the Adams-Novikov E2 page. And that's why you have these Adams-Novikov names here. And the little j, motivic little j, the slices of that is actually catching the alpha families in the effective slices of the sphere. So that's the slices. And then you do the E1 page. That is, you replace every class here using that picture, using the bigraded homotopy groups of the Allenberg-MacLean spectrum and get a three-dimensional thing and organized by co-weight. And the co-weight in this case also shows some two periodic phenomenon. So this is an even co-weight, a representing picture of the even co-weight. This is co-weight, sorry, odd co-weight. This is co-weight 9, and an even co-weight looks like this. This is co-weight 10. And these patterns repeat. You have one more pattern, for example, in co-weight 12. And so after we calculate the D1 differentials, the two periodicity becomes sort of four periodicity with respect to co-weights. So this is a co-weight 9 picture. You have these two parallelograms pattern, and co-weight 10 picture, just single parallelograms, and it's kind of isolated, not many things there. And co-weight 11 has this infinite many patterns. This is an E2 page. And co-weight 12 also has this infinite many patterns. And remember that the differential brings co-weight down by 1, and co-weight 9, co-weight 10, they have too few things so that there are no higher differentials happening on that co-weight pages. But there are higher differentials from co-weight 12 to co-weight 11. And after we calculate this, so what remains in co-weight 12 will be these isolated parallelograms. And in co-weight 11, we'll see this very familiar pattern, this staircase pattern we have seen in the atom spectral sequence. So, yeah, and also you have these arrows, these eta periodic classes, and yeah, that is co-weight 11. And actually the eta periodic pattern, they appears at co-weight 4 and -1 for every n. So when n is 3, that is co-weight 11. And they matches the classical image of J pattern. And the E infinity page matches the pattern in the motivic atom spectral sequence of the R-motivic sphere. So that staircase pattern we just saw. So here I put two pictures side by side. The larger one is the effective slide spectral sequence E infinity page for J in co-weight 11, and the smaller one is the R-motivic atom spectral sequence for the sphere spectrum. And then you see that this looks very similar to this, and these garbage are dropped in the J picture. So the question is, well, is this a surjection? Whether the from the sphere to little j, there's a surjection, and it's actually not. So let me zoom in a bit. For example, if you look at this is stem 7, this green arrow corresponds to this green line in the atoms picture. In this green arrow here in the effective spectral sequence for J, this is a box with 4, meaning that this is Z mod 2 to power 4, Z mod 16. And together with this extension, you form a Z mod 32. But here you have only 1, 2, 3, 4, 4 dots. So here you have a Z mod 16 instead of Z mod 32. That is, in sphere, there is one more dot. So, or in the J case, there is one more dot at the bottom, and that dot has a red modification to this dot, a blue modification to this dot, and that does not appear in the sphere spectrum. Right, so in the motivic case, you don't have a surjection. But still the computation of the little j, motivic little j, using effective spectral sequence is very helpful because it helps us to analyze the effective slide spectral sequence differentials for the R-motivic sphere. So the in the effective, when we are doing the effective slide spectral sequence computation for the R-motivic sphere, and we always compare that to the R-motivic computation, because R-motivic computation is done up to, I think, co-weight 18 by Eva Belmont and then Isaksen, so that we know the answer and we try to produce the effective slice spectral sequence computation. And because of filtration, they're different. So sometimes it's hard to match the patterns. So for example, this is a co-weight 9 picture. This is effective. This is atoms. And you see that in the effective, so both has this 2 parallelograms connected by 2 vertical arrow pattern, but the filtration of these 2 parallelograms get swapped in the atoms and in the effective. So like this bottom one, which has a H1 extension here, is the upper one in the slice. And yeah, so this is a J picture, and the J picture is similar. If you do the effective slice computation for the sphere, then there are many more things to distract you, so that it's hard to get the patterns match because of this filtration difference. And after we did the J computation, then we know, okay, so some filtration swap happen here, and then it gets easier to see like how the slice computation for a sphere compares to the atoms filtration, and it's clearer to deduce the differentials in the effective slice spectral sequence for the sphere. Okay, so yeah, that is the last thing I want to include and the end of my talk. Thank you very much.
All right, let's unmute ourselves and thank Hana for a great talk.
Thank you.
Thank you.
Are there any questions?
I have a couple of questions. So I didn't quite understand, like, it looks like if you tensor these homotopy groups of like the motivic J spectrum or the sphere spectrum, and you look at them rationally, or if you just look at them modulo torsion, is it just one dimensional, like with the normal sphere, or how are the two related somehow? Okay, so what I mean is, like, if you look at the stable homotopy groups of spheres, in degree 0 there's a Z. So when you tensor with and everything else is torsion.
Right.
So in the motivic case, is it just one Z, or are there many copies of Z?
For the sphere spectrum, there are many copies. Wait, no. So first, everything is two complete. I guess I forgot to say. So that is actually a two adic integer, the Z2.
Right.
And for sphere spectrum, the computation, well, there's only one Z in that 0, 0,
Yeah.
and everything else, they're torsion.
Oh, okay. How about for the J spectrum? It's the same. There's only one Z, or there's more than, or Z, two completed Z, or Z, or whatever. So two.
Yeah.
Oh, same.
Right.
Oh, okay. So it's not interesting then. So it's just one thing. Okay. Thanks. I had one other question. I don't know, like I could swap with Martin first, but so is I saw some other talks on this kind of thing, and there's like somehow there's a T structure appears. Do you have anything about, is there anything about a T structure in this situation?
Let me think about what I can say. So there is a T structure on the motivic category. Well, there are different T structures, and the T structure I once worked on is something called child T structure, and that's more like they get different filtrations. So like from a T structure, you can also get a bunch of you can filter the whole category, and for every spectrum you get a tower, and you can get an associated spectral sequence, but that's not the same as this one. And in that T structure, it's more like in the T structure, I'm thinking about the child T structure, it's more like you're filtering everything using very roughly, it's filtering everything using stem minus 2 weight. And in this picture, this is more like filtering everything using stem minus weight.
I see. Okay.
Yeah, that's not rigorous, but
So it's a different filtration, but kind of somewhat related to what you're talking about, but a different filtration.
yeah, right, yeah.
Okay, thank you.
I have a question as well. The charts you showed were all for the effective slice spectral sequence for the R-motivic image of J spectrum, right? And you mentioned the comparison with the motivic sphere. Do you also either use in the computation or conclude things about the comparison with little KO? Do you look at the effective slice spectral sequence for little KO R-motivically?
Yeah. Right. That's turns out to be surprisingly easy because after D1, everything collapsed.
Oh, you still there?
Yeah, can you hear me?
Froze.
Oh, sorry. Yeah. So I was saying that, yeah, we looked at the slice computation for KO.
Sorry, you froze there for a couple of seconds. Can you just take that explanation again?
I think it's you, Martin, but anyways, yeah.
Oh, okay. Sorry. I guess I froze for a few seconds. Sorry about that. So can you repeat that last sentence?
Yeah. So I was saying that we did look at the computation for KO, and it turns out that the KO computation, if you use the slice spectral sequence, it's very easy. It has no higher differentials after E2 page.
Oh, collapses at E2.
Yeah, it collapses at E2.
Wow.
So it's very nice. Well, we know that the atoms computation for KO, it's already an easier approximation to a sphere, but the slice is even easier.
I see. Very nice.
Mm-hmm.
And I had another question. Let's see. What was it? Oh, yeah. The fact that this comparison map from the sphere to J induces a non-surjective map on homotopy groups, bi-graded homotopy groups, that's very intriguing. Can you say something either about, well, the image of that non-surjective map or its co-kernel? So is there something we can investigate in there?
Yeah, I haven't thought about it very hard, but it's only like few things. It's only a small difference. And this difference happens at these like these green, the stem where you have these green lines, that's always for n-1 stem. So
in all other stems, it is actually surjective, or?
Yeah, in all other stems, things are like these staircases in the sphere, and in the J you have these staircases. But yeah, they're the same. I want to say surjective.
But there's still the other part in the bottom corner in the sphere, right? The lower part.
Yeah, the sphere has more things, but the sphere also missed something here in these green vertical lines.
But now it's not just a conjecture. It's known that this comparison map is surjective outside of stems of the form for n-1. Did I understand correctly? Or?
Oh, yeah. Just to be safe, I want to say that this is an observation, but I do not have an argument of rigorous proof of that.
I see. So at this point, there's strong evidence to believe that it's the case, but
yeah,
I think she's saying that the picture matches.
Yeah, fair enough.
Yeah. By comparing the pictures,
it's hard to see on a slide, but I can believe that it would match.
Very nice. Any other questions? If not, let's thank Hana again.
Yeah, okay, I'll ask after. Okay.
Yeah, okay. Let's thank Hana again. Thank you all for attending, and we'll take some overtime questions. If,
I
if
want to
Hana
give
wants
other people an opportunity if they had